What we want to talk about today is how we can use motion to create voltage. And from that, we'll also be able to design a railgun. So in the previous unit, we learned, oh, by the way, voltage induced, that means created by motion. We have a symbol for that. We're going to use an archaic symbol. It's a curly letter capital E, like that, and it stands for EMF. It's an abbrev. EMF is you're going to see this in the notes later. Electromotive force. It's not a force. It was badly named before scientists had a good idea of what was going on. But what we're going to end up with are equations that have created or induced voltage. Oh, got someone coming in here. So we're going to find that we're going to use capital V for the voltage created like from a chemical reaction from a battery. We're going to use this symbol for a voltage that's created through motion. We'll talk about how that's going to work. In the previous unit, we learned that when electric charges move, they produce a magnetic field. And in addition, we learned a magnetic field will exert a force on moving charges. Back in the 19th century, scientists such as Michael Faraday and Joseph Henry were aware of this, and they asked the next logical question. They said, look, if a current produces magnetism, can magnetism produce current? Can we use this to generate electricity? Note, electromotive force, which we abbreviate as EMF because it's not a force. Screen's frozen? Still? Thank you. Thank you, that helps a lot. Electromotive force, or EMF, it's an archaic word that refers not to a force, but to the voltage of a cell. Really, it's used to show induced voltage. So we're going to use voltage and EMF kind of interchangeably. They're both measured in volts. But I'll use this one here to show an induced voltage through motion, so we can kind of distinguish with what's going on. You'll see how it's going to work in the lesson. So, suppose a piece of wire moves through a magnetic field. Well, the charges in the wire will experience magnetic forces. Right-hand rule. Since the electrons in the metal are free to move around, although the protons aren't, the negative charges will move to one end of the wire. So here's an example. We have a wire moving down the page. The magnetic field is into the page. What I'd like all of you to do is put a little proton right there. We're going to follow that proton in the middle of this particular piece of metal. What direction is the proton moving? Well, we're pulling the whole wire down the page, so the proton is moving down the page. So everybody point your right thumbs down the page, please. What direction is the magnetic field? I couldn't get the X's to appear, so I just wrote into the page. So it would be fingers into the page. Which way will the protons get pushed? To the. Which way will the electrons get pushed then? To the. And what you'll end up with is this side of the bar negatively charged and this side of the bar positively charged. What you've done is you've separated charges. And separating charges takes work. You've actually stored some energy in this system. We now have voltage because voltage is defined as the amount of energy per coulomb. If we've done work in separating charges, we have induced a voltage. This is an EMF. How big? Let's look at that. Oh, but first, so we call this voltage induced by motion or motion voltage. I usually use that symbol, EMF. Since the energy in this case, Ethan, comes not from chemistry, like in a Duracell battery, but from motion. In other words, motion can induce a voltage, an EMF. What's the expression? Well, first of all, the definition of voltage was potential energy per coulomb. I gave you the analogy that voltage was kind of like height. Potential energy is work, so we can think of this as force times distance per coulomb. But which force? Well, it's the magnetic force acting on those protons. What's the equation for magnetic force on a charged particle? It's on your formula sheet. Magnetic force on a charged particle. Pardon me? Doesn't matter. I'm wanting the equation for magnetic force on a charged part. I heard it over here. What? Yeah. So now I'm going to use the, instead of V for voltage, EMF symbol, and it's QVB and then times distance over Q. The Q's end up canceling. I also switched to the EMF symbol so we wouldn't have a V and a V and be tempted to cancel them when one's voltage and one's speed. This is the equation to calculate how much voltage we get. Although we typically write it this way, induced EMF is equal to B. D is the length of the wire, and V is how fast the wire is moving through the magnetic field. But again, they all need to be perpendicular to each other for the right-hand rule to have its biggest effect. Can you see where that is on your formula sheet? That should be on the next line after all the magnetic forces stuff, yes? Yeah. Why did I put the perpendiculars in? Well, if the wire and the speed and the field are not perpendicular, we only get a small amount of voltage. So here we have the length of the wire in, next page, this direction, and we have the velocity in this direction. They're parallel to each other. Let's do the same trick we did before. Let's look at a proton right there. Which way is the proton moving? Which way is the velocity of this bar, Jesse? So which way is the proton moving? Same answer. Point your thumbs down the page. Which way is the magnetic field? The protons are still going to get pushed to the right, and the electrons are still going to get pushed to the left. But the wire is so thin, Jacob, we really haven't separated the charges across any distance. We haven't done any significant amount of work. D is essentially zero. So although you technically would get a voltage this way, it's basically zero. Ella will pretend it is zero. So what we have to have is a situation like on the previous page where the length, the velocity, and the magnetic field are all at right angles to each other. That's what gives us our best bang for our buck. So I like example 4. I like example 4. Example 4 is a nice question. It says find the induced voltage across the ends of the moving wire and indicate the polarity. Let's do that first. So looking at this picture, the magnetic field looks like it's down the page. Ooh, V, what does this mean? Our speed is into the page. So the proton is moving into the page. Point your right thumbs into the page. What direction is the magnetic field? Down the page. Which side of the wire becomes positively charged? The left side or the right side? Left side becomes positive. Is that correct, folks? Right side becomes negative. And basically what we've done is we've created the equivalent of a battery, not a chemical battery, a battery of voltage created by motion. How big? Good question. The induced voltage is going to be BLV. I want to make sure that's correct. I don't think that's right. Don't the positives go the other way? Sorry, hang on, let me do this correctly. I stand corrected. You guys are right. I pointed it the wrong way. Wow, too many right-hand rules. What's the magnetic field here? Pretty big, 1.25 Teslas. What's the length? Not 80, 0.8. What's the speed? 5.25. How many volts are we generating across this wire? What'd you get? 5.25 volts? Not much, but some. One application here, it says find the induced motion voltage across the wings of the plane, indicate polarity, and it says assume at high altitude the Earth's magnetic field points straight down. So let's assume that the Earth's magnetic field is in that direction. Let's figure out the polarity first. So again, Jazz and Deep, let's put a proton sitting right in the middle of this plane. Jazz and Deep, what direction is the plane moving? To the, so you point your right thumbs to the right, magnetic field into the page. And I think what's going to happen is this end of the wing is going to become positively charged. That end of the wing is going to become negatively charged. How big a voltage? Well, the induced motion voltage is going to be BLV. Earth's magnetic field is 0.008 at this altitude. The length is 60 meters. Speed is 320. How many volts do we get? What'd you get? How much? Let's go 154. Now, that's a fairly substantial voltage. I don't know what they use it for now, but my understanding is back in the 50s and 60s and 70s, when people used to smoke on planes, they used that voltage to power the little push-in cigarette lighters. So you may have seen those push-in cigarette lighters that get red hot. They use this. Why not? Got it sitting there, may as well use it. I don't know what they use it for now, though. I need to do some research. So how could we actually make this a battery? Well, instead of just moving the rod through the air, let's slide it along conducting wires, because then we'll actually get a circuit. So it says if we conduct the moving metal strip to conducting rails, then the strip will act like a battery, we'll get a current flow. Example 6 says, show that the polarity of the moving strip is like the cell indicated in the right. So they want us to show that the left-hand picture will be the same as a battery with current going in the clockwise direction. Well, let's see. Let's look at our proton right here. Chantal, which way is V? Which way is the proton moving? To the right. So we'll point our thumbs to the right. Magnetic field is out of the page, so I got to kind of bend my hand back. Which way will this proton feel a force? Look at that. We're going to get a current, and now because we've attached wires to it, we'll actually get a current flow. If this was a light bulb, it would light up. So now we've taken it one step further. Now, this isn't a great way to create electricity, because as soon as you reach the end of the railings, you're done. You'd have to have an infinite long rail to continue to pull something along to get that charge. But it's a start. It's a start. But now it's going to get weird, Kane, because as soon as we're moving this to the right, as soon as current starts flowing down, now we don't just have charges moving to the right, we also have charges moving which way? Starts with letter D. Point your right thumbs down now. Magnetic field is still out of the page. Got to go like this. Which way will this down? Magnetic field out of the page. Which way will there be a force on the wire? To the, there's going to be a force in this direction. In fact, let's do it right here in example 7. If we have a magnetic field coming out of the page, current going down, you'll actually feel a force tugging against you, and that is there. That force shows up whenever you're trying to generate current. If you've ever used one of these crank-powered flashlights or radios, when you turn it, you might notice it doesn't turn very easily. Why is that? You're actually feeling that force against you, that FB. It's a little different because it's a coil. We'll talk about that in a couple of days. But you're feeling that force resisting you. It's a consequence of the law of conservation of energy. You can't get anything for free. You want to create some electricity? Fine, you're going to feel it opposing you. So we have this weird situation that as soon as this starts to move sideways and as soon as current starts to flow, now you not only have the charges moving sideways, you have them moving up or down. So you have two right-hand rules. Example 8. The strip below is 12 centimeters long. Nice try, Dueck. 0.12 meters. And it's moving at 4.7 meters per second. The external magnetic field is 0.08 teslas, and the resistance of the rail circuit is 0.025 ohms. It says find the induced motion voltage. We can do this right up here. The induced voltage is going to be BLV. It's going to be 0.08 times 0.12 times 4.7. How many volts will we get here? I don't think you're going to get terribly many. Jacob, what'd you get? 0.45 volts. Meh. Well, okay. Jacob, what's B want me to find? Current is voltage divided by resistance, but the voltage is going to be the EMF. It's going to be the induced voltage divided by the resistor. So it's going to be 0.045 divided by, they did tell me the resistance of this circuit is 0.025 ohms. How many amps? What'd you get, Jesse? Oh, that's a little more substantial. That's a decent current. Okay. Joe, what does C want me to find? Keep reading. On the strip, on the wire, magnetic force on a wire, F equals, what's our equation for magnetic force on a wire? BLV? This is voltage, not force. It's not F equals. Bill! Yeah. F equals Bill. It's going to be 0.08 times 1.8 times 0.12. How many newtons of force will we feel tugging against us? 0.17? So 0.17? Anybody else? 0.017. Anybody else? After that, I want to make sure. No? Yeah, 0.017. Now, I want you to notice, what if we tried pulling this faster? Well, that would make V bigger. So what would happen to this answer? Get bigger. What would happen to the current if this number got bigger? Bigger. What would happen to the force opposing you if the current got bigger? The harder you pull, the harder nature tugs back. It's a consequence of conservation of energy. You can't get free electricity from nothing. You got to work at it. Okay. The next thing that Faraday and Henry thought of is they said, well, what if instead of a wire moving through a magnetic field, what if we pull a coil or a loop through magnetic fields? I've got a rectangular loop here. Let's put a proton right there, right there, right there, and right there. And let's look at each of these chunks of wire. On the top chunk of wire, what direction is the proton moving? Well, what direction is the loop moving? To the right. So you point your right thumbs to the right. Magnetic field is out of the page. This top proton will get pushed down. Is there anywhere down for it to go? No. And the reason is because this section of wire and this section of wire aren't perpendicular to the velocity. They're parallel to the velocity. So we're not going to get much from those two sections of wire. But the front section will give us something. We have the that way, magnetic field out of the page. A proton in that front section will feel a force, will cause a current in that direction. What about a proton on the rear section? Well, it's moving to the right, magnetic field out of the page. A proton in the rear section will feel a force that way. And what you'll end up with are two identical opposing currents. In other words, everything cancels out. You get nothing. Everything cancels. So that was their next thought, was maybe a loop is going to work. Nope. Rats. But believe it or not, we're very close to designing a railgun. What if instead of us pulling to get voltage, what if we supply voltage? Can we get motion? So example 10, in this circuit, the wire strip here is initially at rest, and we've hooked up a voltage supply over here. So let's draw in the current. In the wire, Amber, what direction is the current moving? So everybody point your right thumbs up the page. What direction is the magnetic field? So out of the page, I've got to go, let's see, I got to do this right. Let's do it. Up the page, magnetic field out of the page. What direction will the wire feel a force? The wire is going to feel a force, a B-I-L, in that direction. And it'll start to speed up. So it says in this circuit, the wire strip is initially at rest, and there's power supply in the circuit. What's the direction of the current? Initially, it's counterclockwise. What's the direction of the magnetic force on the strip? To the right, right? And what happens to the strip? Well, it starts to accelerate because it's got an unbalanced force acting on it. So this is one type of railgun. Put your pencil down, look up. What do I want, Mr. Dueck? Electromagnetic railgun. Come on, computer, you got this. So this is a railgun firing a hypervelocity projectile. I think it's hitting 7 times the speed of sound. It's moving really fast, so in slow-mo, now, these were really trendy in the 80s. The problem with these for a railgun, it has to be really, really long by definition, because the longer the projectile is attached to the rail, the longer you have the force applied to it. You watch the news, modern warfare, are we into large, unwieldy things that aren't mobile? Is that the way we fight nowadays? Not so much. So this was a big issue. You're all too young to remember, but in the first Gulf War, which happened in 89, I think it was, 89, 90, at that time, the U.S. had invaded Iraq again, or for the first time. They were blockading ships that were carrying long pipes that Iraqs were saying were for oil derricks and oil piping, but the suspicion was it could be used to build a rail gun. What's the next one? Oh, how to make a simple rail gun. How, H-O-W.
Railguns are simple devices that can accelerate a projectile to very high speeds. The Navy railgun has the record, accelerating a projectile at a speed of Mach 7 or more than 5,000 miles per hour. A simple railgun can be made with just 2 speaker magnets, a couple of conducting wires, a 12-volt battery, a resistor of 0.5 ohms,
You do want to have a resistor in your circuit, otherwise the current goes up into heating the wires, and red hot wires is bad. But otherwise, you can try making this at home.
and an object that is a conductor, but that is also non-magnetic.
Stainless steel works pretty good.
When we connect the battery to the wires, the electricity will flow to the first wire, then will go through the projectile, and then will go back to the battery through the second wire.
So we want the force to be to the left. So point your palm to the left. Okay. If the magnetic field is pointing upwards, then we would want the upper wire to be positive so that the current flows that way. I don't know which way the magnetic field is pointing, but let's find out.
As we can see, the projectile is in contact with the rails. When the current flows, a magnetic field is generated. We use magnets to increase the field. The interaction of the magnetic field and the current generates a force in the projectile.
There's BIL, Bill.
This is known as the Lorentz force, and its direction depends on the directions of the magnetic field and the current. Now let's power our railgun.
What if we reverse the
If
current?
we invert the polarity of the battery, the Lorentz force will change direction and will push the projectile to the right.
Flip the current. Easy peasy.
In
Nice little railgun. But it gets a little weirder. Okay, example 11. So we have our initial current. I'm going to do that in blue. And inside the wire, the current is moving up the page. So we would point our thumbs, right thumbs, up the page. Which way is the magnetic field? Out of the page. And so we have a force to the right. But now what just happened, this wire started moving in which direction? To the, starts with the letter R. So not only are protons moving upwards, now we also have protons moving sideways to the right. Everybody point your right thumbs to the right. Which way is magnetic field? Still out of the page. So like this. Which way are the protons going to feel a force? The protons are going to feel a force down, opposing the source current. And the faster the gun goes, the more the source current is getting canceled out by the induced voltage, the induced EMF. And when they equal each other, that's the maximum speed of your railgun. The maximum speed of your railgun is when the voltage, the EMF that you induce here, equals your source voltage. So, as the gun speeds up, what happens to the induced voltage? The EMF increases because speed is increasing. Right? EMF equals BLV. So what happens to the current? The net current decreases because now you've got some protons getting pushed against the source current. What happens to the magnetic force? Well, if the magnetic force is Bill, if I get smaller, what happens to FB? If I get smaller, what happens to that? Decreases. So what happens to the speed? A gets smaller and eventually A equals 0. Doesn't mean it comes to a stop, it just means it stops accelerating. And when that's the case, you've hit the maximum speed for your railgun. And it's pretty trivial to calculate what your maximum speed is. We can do this pretty easily. So again, we have a situation, we have two applications of the right-hand rule. The first right-hand rule application is from the source current that causes the bar, the projectile, to start to move in the first place. But now that it's moving to the right, now we also have protons moving to the right. There's a second right-hand rule. And again, this is a consequence of conservation of energy. The universe isn't letting you get anything for free. Because if the protons moved in the opposite direction, this would speed up on its own naturally. You'd be getting free energy. So it says explain your answer using relevant physics principles. A couple applications of the right-hand rule. So This setup, though, has two applications. Number one, it's seen as a means of launching vehicles from the International Space Station without the need of rocket fuel. So you would have large solar cells to get current. We have that. You would have electromagnets, and the ship itself would be your conducting bar. So if we turned on the current inside the ship, current would be going down the page. So everybody point your right thumbs down the page. What direction is the magnetic field? What do those X's mean? Into the page. Which way will the ship feel the force? And you'll be able to launch it without using any kind of rocket fuel. And especially in outer space, Ella, because Newton's first really takes hold in outer space, you could launch it quickly if you wanted to with a big force, but even just a tiny force, it'll move and then it'll just keep going in a straight line at a steady speed, and you don't have to have them fire their rockets right near the space station, because what could go wrong with that? They don't have to. The other application, if I scroll back, what this means is this particular gun will be at its coolest when it's at its fastest. Because what causes metal to heat up? Current. When is the current at its minimum? The current is at its minimum when it's no longer accelerating, when you hit the equilibrium point. And so this also has an application in electric motors. Now, in electric motors, it's a coil spinning. We'll look at that in a couple of days. But the faster it spins, you generate a back voltage in the same way as we're generating a back voltage and a back current here. So we'll look at that in a couple of days. We'll do a whole lesson on back EMF. Example 12. As the strip continues to speed up at a lesser rate, the induced voltage will continue to grow. Yeah, because BLV. What happens when the induced voltage is equal to the supply voltage? What happens when V supply equals the induced voltage? Well, let's look at this. So initially, we would have current going this way. But as soon as it starts moving to the right, we're also going to have current going this way. What we would have are essentially two opposing batteries. Who remembers from our circuitry unit, if you have two batteries facing each other, 6 volts this way, 6 volts this way, what's your net voltage exactly as a number? 0. What happens is you get okay, if your voltage is 0, what's your net current? Because V over R. So what's the magnetic force if it's Bill? So what's the correct answer? A, B, C? If F is 0, what's going to happen? Yeah. And that'll be the maximum speed of your railgun. Just for giggles, let's get an expression. So what is the expression for the maximum speed? Well, that's when the source voltage equals the induced EMF. Source voltage we can think of as I times R. Induced EMF we can think of as BLV. What does this want me to get by itself? V. And you can start to see why we introduced this EMF symbol, because this V and that V and that V, it'd be easy to get all confused. Okay, let's get the V by itself. The maximum speed is going to be I times R divided by BL. As far as I'm concerned, there's 5 variables. If I gave you any 4, you could find the 5th. I could ask you to find the maximum speed, or I could tell you the maximum speed and say, okay, what was the source voltage, I times R? We'll come back to the video in a second, but let's do one with numbers. Example 14 says, for each instance pictured below, find the induced voltage, the net voltage, the current and direction, and the magnetic force. Let's just draw a line down the middle of the page. We'll do these kind of simultaneously. So let's do part A first. The induced voltage is BLV. Okay. The first one is easy, because what's V in the first diagram? So what's the induced voltage in the first diagram? You got a source voltage, but you have no induced voltage. In the second one, we have 0.35 times 4.1 times 64. And as a direction, that would be opposing the source voltage. It will be going up. How many volts? 91.8. Okay. Caden, what's B want me to find? The net volt, well here, since the induced voltage is 0, the net voltage is just the source voltage, 320 volts. But here, it's going to be 320 take away 91.8 because they're opposing each other. Which is what? 228. So at this moment, the net or the overall voltage is smaller. Ethan, what's C want me to find? Okay. Current is V over R. It's going to be 320 divided by 8.5. What'd you get? Ethan, what'd you get? 37 point. Here, current is going to be V, but it's the net voltage over R. So it's going to be 200, it wasn't 228, what was it? 220 something point something. Okay. So I'll write 228, but I'd use my answer button. Divided by 8.5. How many amps now? Carter, what'd you get? Folks, you're zoning out. You got to type the stuff in. Sorry? 10.8. Anybody else? That seems low to me. 26.8. Make sure you use the net voltage. Ethan, you don't have a headphone in your ear, do you? That would be silly. Thank you. Ella, what's D want me to find? On the wire? Hey, that's Bill. So it's going to be, I've scrolled down. What was the magnetic field? 0.35? Current, 37.6. L was 4.1. Point 35 times 37.6 times 4.1. So initially, I get a force of 54 newtons. Yeah. But as it speeds up, the force is going to get less and less and less and less, the net force. Oh. Yeah. I don't know. I got 53.956, didn't I? Am I right or am I wrong? Yeah. 0.35. Here the current is 26.8, 4.1. And I get 38.5 newtons. And as it goes faster and faster and faster, the net voltage gets smaller, the net current gets smaller, the net force gets smaller until you hit a maximum speed. What's the maximum speed? When V source equals induced voltage. What's your homework? You can try number 1 is good, 2 is good, 3 is good, 4 is good. 4b is asking you to find the power required. Well, power equals V times I. So if you know V and you know I, you can find the power required to go at a constant speed, to go at your maximum speed. You can skip 5. 6 is good. 7 is good. 8 is good. You can skip 9. And let me go like this. Pause for a second.